Hi, everybody, and welcome to our 14th and final lecture of Environmental Sciences 347, Climatology, going to climate change and public policy. And arguably, this is going to be the least exciting of all the lectures because we're not going to get into what we ought to do about climate change, but what we will do is take a brief history of how we've gotten to the point we've gotten to right now. Right now being 2021. So really looking back around 30 years since the science started to become a little more strong and foundational. So stepping back from as a global society, the current scientific assessment was really well founded at the end of the 80s, early 90s, that global warming is real and unequivocal, and that human activity is generally responsible for the warming since the mid-20th century, with a lot of that even further, let's say since about the 70s and 80s. As we got into the late 70s and 80s, the acceleration of planetary warming really began to take shape. So if you want to go back and look at some of the scientific assessments, there are any number of scientific bodies you can go to. For very popular ones in the Western world, the American Meteorological Society, the American Geophysical Union, the National Academy of Sciences here in the United States, and of course the Royal Society of Great Britain. And the Royal Society has some of history's greatest scientists all the way back to Newton. So these are societies that are very well respected and very tough to fool anybody in these kinds of societies. So if you're curious, take a look, Google some of these. Google, scientific assessment of climate change for any of these, and you'll largely get the same responses. So to take on a problem this daunting and this truly global in perspective, we look to the past to see if there have been any analogies for how we handled something like this. And there aren't a lot of good ones. One of the best ones, though, goes back to the Montreal Protocol of the late 80s and early 90s. After the scientific community reached the conclusion that chlorofluorocarbons are basically chemical propellants that were found in traditional aerosol cans, got into the stratosphere, mixed with nitrogen, and at very low temperatures spawned chemical reactions that destroyed ozone. The scientific community was able to very easily convince the governments of the earth that we need to stop making these things very quickly, or else we're in real threat of damaging our protective ozone layer, again, in the stratosphere. Ozone down here at the troposphere level is caustic to human lungs, but up in the stratosphere, we need it very badly to block most of the upcoming or the incoming ultraviolet radiation. So required the worldwide phase out of the CFCs beginning in the mid-90s, and it's worked for the most part. The ozone hole hasn't repaired itself, but it has stabilized. So we are no longer seeing any ozone depletion in the stratosphere at the South Pole. That's where it started, and part of the reason why we're okay is that we did take action back in the mid-90s, or else some of those CFCs would continue to build, move away from the South Pole into the mid-latitudes, where we could do a lot more damage to people, where more UV would get in, so you'd start to have more skin damage. You would start to have more incidences, not just of sunburn, but things like cataracts, things like that, more skin cancers, those types of things. So for the large part it worked, and a full restoration of the ozone layer is still probably a few decades away, but the actions that we did take 25 to 30 years ago have already started paying dividends today. The thing with the Montreal Protocol is that it only affected a very small segment of national economies, whereas when we look at greenhouse gases, this basically powers the entire global society. So it's a much, much bigger problem to tackle. However, it does give us some kind of framework or some kind of analogy to take on a bigger scientific problem, whether it's chemistry, physics, something that has long-term negative repercussions for humans and society in general. What can we do? What can we learn from the Montreal Protocol from the late 80s and early 90s that might be able to apply going forward? So we start with the first real global meeting about this issue, which is 1992 in Rio de Janeiro. The United Nations Conference for Environment and Development issued this, precautionary principle. Basically, when an action causes a threat to everybody, we need to take action, even if we're not 100% certain about how X affects Y, or the cause and effect relationships. We are fairly certain, but they haven't been 100% established. But it's like I've said before, sometimes you see a jigsaw puzzle and you see how it's all going to come together, even if you only have 80 or 85 pieces out of a 100-piece puzzle, you see where it's going. And that's why it was decided that some action should be taken. You need to balance environmental issues, of course, with social and economic concerns. We don't want to go back and live in caves again like we did millennia ago. So we must consider the needs of humans now, as well as think about our descendants. How are they going to live? What kind of environment are we leaving for them? So with all that in mind, the UN Framework Convention on Climate Change was established in Rio in '92, with the goal here of stabilizing greenhouse gas concentrations in the atmosphere that would prevent dangerous interference with the climate system. Basically, too much warming. Precisely too much warming was still a little harder to tease out back in 1992. But as time went on, it became more obvious that the human's impact on the climate system was growing. Kyoto in 1997 came along, and this is the first kind of real, because you call it, we always hesitate whether you call it a treaty or agreement or whatever, but 39 nations agreed, in concept anyway, to reduce emissions of 4 primary greenhouse gases. And then with that, we started seeing a lot of the countries in the European Union ratify it or accept this treaty or agreement. The United States was not one of them. We were noticeably absent from this, although there were a few regional initiatives taking place. The U.S. was largely absent from the Kyoto Protocol. So in the EU, they adopted a cap and trade system in 2005 to regulate greenhouse gas emissions. This also led to the concept of carbon offsets and the like. But in the U.S., the support just wasn't there. The public was much less convinced of any kind of real global warming threat and was clearly more interested in the economy. So things went quiet for a little while after that until the next real news-making event was Copenhagen in Denmark in 2009. The goal here was to draft a new international treaty because the Kyoto one was going to expire in 2012. Of course, it has expired. The result from that was the Copenhagen Accord, which was the framework that first gave us this whole 2 degrees Celsius concept. The goal to limit the rise in the global average temperature to 2 degrees Celsius above the pre-industrial level by 2100. And by pre-industrial, we mean the very late 1800s. We've already seen it go up about 1 degree Celsius since then, so we're kind of running out of time if we're going to meet that goal. The problem with this is that it's not legally binding and it doesn't specify any kind of targets. It's just like, we kind of want to do this. Well, that's great, but there's not a lot of framework for it. One of the things that came out of this was the term climate sensitivity. And we touched on this in a few lectures ago, that the climate sensitivity, which sounds kind of indefinite, does have a quantifiable meaning. It's defined as the equilibrium change in the global mean annual surface temperature caused by an incremental downward infrared flux that will result from the sustained doubling of atmospheric CO2. So basically, how much does the average temperature change if you double CO2? Looking at, and we say pre-industrial, so we think about 350 parts per million. If we were to double that to about 700, what does that mean? How much does the planetary average temperature change if we run it up to 700 and then wait and then shut it down at 700 and then wait for the planet to come into equilibrium again? And that's known as the climate sensitivity. And this is a figure that is still argued an awful lot in climate circles. And it's certainly not insignificant, but some climate models and some modelers and some scientists are going to have different aspects on what that number is. So then that brings us to Paris in 2015, the Council of the Parties, or basically the next one of these global meetings from the UN. And this particular accord kind of reemphasizes we want to keep the temperature below 2 degrees Celsius above those pre-industrial levels. But countries should also make an effort to limit the temperature to 1.5 degrees C above the pre-industrial level. And then in 2018, there was a special report by the IPCC, Intergovernmental Panel on Climate Change, that said global warming at 1.5 is going to be significantly different than global warming at 2C. There will probably be more poverty, more extreme heat, higher sea level rise, more habitat loss and drought at 2 degrees Celsius versus 1.5 degrees Celsius. So to achieve this objective, 186 countries that are responsible for more than 90% of the emissions submitted reduction plans or targets known as INDCs, or the Intended Nationally Determined Contributions, prior to the conference. And these targets outlined each country's kind of commitment to curbing emissions, whether it's through preservation or carbon sinks, through 2025 or 2030, including carbon cutting goals. So basically, how are you going to do this? What targets are you going to meet, and how are you going to do it? So this is kind of the first time this was really involved or put into writing. And these are things that are still kind of hashed out today, with the next meeting of the parties coming up in Glasgow, Scotland this fall being November of 2021. So scaling back from the global level, looking at how things are now in the United States. And we have seen more of a change in opinion over the past 5 to 10 years for sure. The most recent public opinion maps, these are from some of my colleagues at the Yale Center for Climate Communication and the George Mason Center for Climate Communication, a couple other institutions as well. The estimated number or percentage of adults who think global warming is happening. And nationwide in 2020, this number runs about 72%. The darker reds showing you where those numbers are higher. And, if you look at this long enough and you look at this closely enough, you start to see little patterns pick out. You could start to see where there are universities. You could start to see where there are cities. You could start to see places that are a little more liberal, some places that are a little more conservative. That begins to show up in the data, no question at all. But as we look back to 2008 and how public opinion has changed, it's funny, after the financial crash in 08-09, people really cared a lot less about this because they're just trying to make ends meet. And then as things began to come back, we started to see a greater understanding and acceptance of mainstream climate science. So, 3 out of 4 people in the country, finally acknowledge that it's happening. 6 out of 10 still think it's human cause, and there's still a struggle that a lot of people don't understand that there is a very strong scientific consensus. And you're always going to have people who make a lot of noise and say this isn't happening for whatever reason. They have other reasons. It's not just that they don't accept the science. They're largely financial reasons that they don't accept the science. It's hard to convince somebody of something when they make their money not knowing about it, is the old term. So we still see a lot of that today, although the impacts aren't as strong as they used to be. So There are a number of political responses, and we're just going to kind of go through this real quick. You want to consider a problem in its entirety. When you've got one component of the Earth system that's disturbed, other parts are affected. You tinker with the ice caps, that's going to affect other things. And the climate science community is in large agreement that this poses a threat to humanity and needs to be addressed. This isn't just a bunch of polar bears. This is a threat to our way of life, our sustainability, our ability to feed a large population, growing population, water resources, these kinds of things. So theoretically, you want to make your decisions based on the long term. Unfortunately, we don't see that, especially here in the United States. A lot of people just want to get elected again. Fair or not. So legislators tend to address local concerns more than larger concerns. So oftentimes we're not looking at the bigger picture as we should. So small changes are going to be made in existing policies or program. That really appeals to policymakers because it makes fewer demands on them. They don't have to make a tough decision. You make a small change here or there at the local level, you don't have to make a tough decision that can get you thrown out of office. Unfortunately, it's just the way of the world right now, at least in the United States. Economically, the issue here is that we keep relying on current technologies. They're not going to reduce greenhouse gas emissions at the same time allow economy to expand. And when I say current technologies, I mean natural gas and oil. Coal is already on a nosedive because of natural gas. And natural gas is certainly, some people certainly call it fossil gas because you burn it and you give off CO2, just not quite as much as you do when you burn a coal or oil. But to that end, we're going to have to, at some point, improve economic efficiency, include energy efficiency, so that the resources are used in the best way possible to meet consumer demand. So, two ways. There's two big frame of references here. One is the free markets, where the resources are allocated and prices are established based on individual voluntary exchanges amongst consumers and producers. And this goes part of this cap and trade. It's kind of nudging a free market. We're introducing some kind of market capitalism. All right. It isn't entirely free, but it does give you a little supply and demand thing going on. All right. Drawback being the complete information about the price and availability is not always transparent. And not all consequences are shown in these market transactions. The other way is you just regulate everything from the government. And I see the government, that's kind of a scary term when somebody just says the government. But the government is people. The alternative to the free market system, which we've already seen in a lot of Europe and starting to see that in Asia as well. The critics say that this is going to discourage efficiency and innovation. And that may be the case in some locations, but it depends on what kind of government you have. It's probably never, the reality is that it's not either or. A little bit of each of these is probably the way to go, but figuring out exactly how that is going to work is still anyone's guess. So there is no easy answer. Economically, scientifically, this is a multidisciplinary problem. We need to have a lot of people weighing in from a lot of different directions looking to solve the issue. And it can be daunting for sure, but I also encourage people, don't let that get you down. We have done big things. I say we, humans, especially even here in the States, we've done some big things pretty quickly in the past. If you think about how quickly we went from horse and buggies at the turn of the 20th century to automobiles, that all happened in about 20 or 25 years. By 1920, 1925, horse and buggies were gone. They were gone. Think about how we've introduced electricity into the United States. Back in the 1920s, electricity was not common. You couldn't just turn the light on. But by the 40s, that was the case. Most people had electricity. Even, of course, that was lead up to World War II. But most places had electricity by then. And even more recently, these things. I mean, I'm 51. I didn't have anything like this growing up, obviously. Just in the year 2000, smartphones, there were very few smartphones. There were these big, bulky phones where if you bought 30 minutes of airtime, it cost you $50. And now, there's more computing power in a smartphone than there is that was used to get to the moon back in 1969. So the short version is this is doable. We need to put our minds together. We need to have, people with some good ideas, bounce ideas off of one another, and figure out a way to do this. And yes, renewable energy is certainly one thing. Solar, wind energy, that's the hot thing right now. And that is absolutely part of the issue. But and also, we need to figure out a way to increase efficiency, increase electrification of transport, and figure out a way to generate electricity, generate energy overall, without setting carbon on fire, as my friend in Colorado State says. So that's it. The end. This can be accomplished. It's going to take some work, but it can be accomplished. I don't like these doom and gloom, we're all going to die in 30 years mess, because we're not. Planet's not going anywhere, but we need to think of some ways to work through this problem. It's a big problem, but we can work through it. So I'm hoping that everybody comes away from this course not having all the answers to everything, but giving you a good rudimentary knowledge, a fundamental knowledge of how the overall climate system works, how we know climate is a certain way in one part of the globe versus another, whether we look at orbit of the Earth around the sun, tilt of the Earth around the sun, the fact that we have oceans, we have ice, we have land, all that stuff moving together in very reasonable, predictable patterns, and then how we are beginning to modify the atmosphere in these last 100 years and what the repercussions of that are going to be, not just for the natural environment, which is very important, of course, but what's it going to mean for us as humans as well. So with that, I thank everybody for attending the course, watching the course. Hope you got something out of it. Best to everybody, and take care.